In this video, we're going to look at how to do titration between an acid and an alkali. If you think back to year 10, we looked at neutralization and we looked at hydrochloric acid. It's a very simple neutralization. Hydrochloric acid, HCl is its formula. Hydrochloric acid reacting with an alkali, sodium hydroxide, a very common alkali. That's the titration we'll talk about today in a moment. Sodium hydroxide, and when they react together, they make sodium chloride. And water. An acid and an alkali makes salt plus water. So that's the reaction. So the hydrochloric acid reacts with sodium hydroxide, NaOH, to make NaCl and H2O. Now these are all in the liquid state or the aqueous state. So water is liquid. Sodium chloride that's produced will be aqueous. So sodium chloride dissolved in water. The sodium hydroxide is aqueous, and so is the hydrochloric acid. So everything there is aqueous. So the first question here: why is it essential that neither reactant is present in excess if you want to produce a pure sample of the soluble salt? The reason is this: if you have too much hydrochloric acid or too much sodium hydroxide, when one of those reactants runs out, there'll be spare of the other. So you'll have the sodium chloride, but that will be polluted with the leftover reactant, and there's no way of separating it. So there's absolutely no way of separating it because they're all dissolved together in the same solution. So why is it essential neither reactant is present in excess? If a reactant is in excess, that means there's too much of it, then this leftover reactant will be mixed with the sodium chloride. Now in year 10 we looked at titrations, so we reacted exactly the right amount of hydrochloric acid with exactly the right amount of sodium hydroxide. Now we're in year 11. We come back to titrations again because they're very useful things to do, because with a titration we can work out really quite accurately the concentration of an acid or an alkali if we know the concentration of the other one, by doing a titration, working out exactly how much is needed, and then doing a calculation. So this is a big part of year 11. This is what we're going to talk about now. So first off, we need to know how to do a titration. Write a method and draw diagrams to fully explain how to carry out an acid-base titration to determine the concentration of a solution of sodium hydroxide. So the sodium hydroxide we do not know the concentration of. The acid we do know the concentration of. What apparatus would we use? Well, we're going to do a titration, as I said. To do a titration, we need a burette. A burette is a very, very long, thin glass tube, like so. And at the bottom of it, there's a tap that will let drop by drop the acid through. So we can show a tap by putting a circle with a cross through it. Underneath that, we're going to have a conical flask. Okay, a conical flask, like so. Looks like a bit like a cone, hence conical flask. And into that conical flask, we will put the sodium hydroxide. On that conical flask, we will put it on a white tile. So we can see the colour change nice and easily. So this is the burette. And that's our conical flask. Now we are going to put the alkali into there with a pipette. Okay, the pipette. So we will measure our alkali out into the pipette. The pipette is is a thinner tube even than the burette. It has a little bulb in the middle, so we can just get the required amount of sodium hydroxide into there. Okay, very thin. Little glass. These are all glass, very fragile. Okay, and there's our pipette. We will measure out our sodium hydroxide. They have a marking on the top here, the pipettes. So our sodium hydroxide will be in there, which we will have sucked out of a beaker by the side, and then we should be putting it into the conical flask beneath. Also in here, we will have our sodium hydroxide, which we've measured out with the pipette, but we will also add to that phenolphthalein indicator, which will turn pink in the alkali. So that's the apparatus. Now the method. So we'll quickly write that down there. I shall bullet point this up. Fill burette with acid. 2. We're going to accurately pipette 25 centimetre cubed of sodium hydroxide into the conical flask. 3, we're going to add phenol phenolphthalein indicator to the flask. 4, we're going to put the conical flask under the burette on a white tile. 5, we're slowly going to add the acid, swirling all the time. We swirl it to make sure the acid reacts with the alkali nice and quickly. 6, we're going to carry on doing that, but we're going to stop when the phenolphthalein changes from pink, and it goes from pink to colourless. That's important, pink to colourless. We then record the results. So 7 is record the results and repeat until results are concordant, or similar in other words, and then we can average the results. And there is our 7 steps to doing a titration. The symbol equation for this we'll just quickly do down here. This is the hydrochloric acid, HCl, that's aqueous, plus sodium hydroxide, NaOH, aqueous. That's the alkali, that's the acid. They react together to make a salt, NaCl, aqueous, and water, H2O. Liquid, water's a liquid. This equation is already balanced. One hydrogen there makes 2. That's the 2 hydrogens there. One oxygen, one chlorine, one sodium, one sodium. The equation is balanced. So what we're going to try and do here is a titration, an accurate titration to determine the concentration of the sodium hydroxide. I've pipetted out 25 centimetre cubed with this long glass pipette, and I'm now letting that drop into the conical flask here. This sodium hydroxide, we don't know the concentration of it, so we're going to add acid to it until it goes neutral. So the last bits of sodium hydroxide are dropping out of this pipette now. There'll be 2 drops left in the bottom. Now we need to get one of those out. The other one stays there because that's measured into the reading on the pipette. So where we get the one out, we just touch it on the surface of the water and it drags out that 1 drop. So that's the sodium hydroxide in the conical flask. We're now going to put that underneath the burette, which I've already filled with acid. And we're going to add some phenolphthalein indicator. A couple of drops of that, well, more of a bit of a tip of that. Okay, now I've already done a rough titration, so I know the neutralisation point is about 27 centimetre cubed, so I'm going to quickly run in, well slowly I should say, some acid to that while swirling all the time. The swirling keeps the reaction going, makes it happen nice and quickly. I'm going to slow it down a little bit now so we're getting closer to the neutralisation point until we eventually go drop-wise in a moment. So I would expect the neutralisation point to be quite soon, so I'm going to slow that down even more. Now it's quite a quick burette this. Now the phenolphthalein will go colourless when the neutralisation point is going on. It's getting quite close now. So you see it's going colourless. It's not quite there. I think maybe just one more drop. Let's give it a quick swirl. We'll see how the colour's lightened. Okay, because I've already done that rough titration, I know pretty much where that neutralisation point is. So I can slow it down at the key point to try and get an exactly neutral solution. It's only when we get that exactly neutral solution, I just want one more drop, I think. There we go. Is that gone? Let's have a slight pink tinge to it, so maybe one more drop. One more drop just to, there we go. I think our solution, maybe still a slight pink tinge to it. This is why the white tar is so useful, because it gives a contrast between the colour. So possibly just that one extra drop. Right, there we go, that's now neutral. So our neutralisation points, let's have a quick look on the burettes. If we lift the camera up to see that. Should be able to see, hopefully if we can get a focus on that. Let's bring it a little bit further away. Just on the 26.6 line. It's not particularly well focused. But 26.6 is the neutralisation. Right, and that's how we titrate an acid against an alkali.